Holiday Science, Bernoulli and your Christmas tree. Are you tired of watering your tree like this? There's a better way. We're going to use science to water the tree.
Science?
Yes, we're going to use Bernoulli's equation.
We're going to burn something.
No, not Bernoulli. We're going to use his math. For those who just want the punchline, the tree is continuously watered from a plastic box reservoir that contains a siphon tube to the tree basin. But now, for the fun part, the math! What does Bernoulli's equation tell us about keeping our tree watered? Well, first, this equation is applicable along a streamline. Second, we assume we have an ideal fluid. What does an ideal fluid mean? It means we assume the fluid is incompressible, has no viscosity, and the particles do not rotate around their center of mass. In simplest terms, Bernoulli's equation is a representation of conservation of energy. That is, along a streamline, the pressure energy plus the kinetic energy plus the potential energy is constant. In symbols, we can write this in terms of pressure. P for static pressure, 1/2 density times velocity squared as the dynamic pressure, and density times gravity times distance from our reference plane is the hydrostatic pressure. In our equation, P is the pressure, rho is the density of our fluid, V is the velocity of our fluid, G is gravity, and Y represents the distance from our reference plane. Let's draw our watering system. Here is our tree stand, here is our reservoir, and here is our tree. Now, drawing the tube between the tree basin and the tree reservoir, and drawing all our water particles. Let's mark our locations of interest. Top of the water levels in the tree basin and the top of the water level in the reservoir. Our pressure is the same at both locations. That is, it is equal to the atmospheric pressure. Also note that the density is the same in both locations. That is, it is the density of water. The velocity could be different in both locations, so we mark it as V1 and V2. And finally, we mark our distances, Y1 and Y2. Since we have conservation of energy, we can say Bernoulli equation at location 1 is equal to Bernoulli's equation at location 2. Since pressure and density are the same on both sides of the equation, we will just write P and rho. No subscripts are necessary. Let's do the math. We can subtract P from both sides so they cancel out. Since the water will eventually stop flowing, in equilibrium, the velocity at both locations will equal 0. Oops, I got a little L crazy in equilibrium. So we can cross out those terms, simplify our equations. Cross out density and gravity from both sides, and we see that when we reach equilibrium, the heights must be the same. Now, on to building our tree watering system. These are the things you will need: a reservoir for water, a hose, the one I have has a pump to start the siphon, and a knife or tool to make a hole in the lid. So here you can see I made a hole in the lid for the hose, and the hose goes over to the tree basin. The hose is held into the tree basin by a couple of clamps. Inside the box, you can see the end of the hose is held down by a couple of rocks. Not the best solution, but will do for now. You will need to be aware of the water levels in your reservoir. Too high and you risk overwatering and flooding. Too low and you will lose your siphon. I usually mark on the side of my bin appropriate maximum and minimum points. And that's it. Let me know in the comments if you are inspired to simplify your Christmas tree watering, or if you already do this. And finally, you could decorate the box to look like a present if you would like it more festive. Happy Science-y holidays!